All right, so properties of special parallelograms. We're going to talk about rhombuses, rectangles, and squares. So a rhombus is a parallelogram with 4 congruent sides. A rectangle is a parallelogram with 4 right angles. And a square is a parallelogram with 4 congruent sides and 4 right angles. You can use the corollaries below to prove a quadrilateral is one of the above without first proving that the quadrilateral is a parallelogram. So corollary 7.2, a quadrilateral is a rhombus if and only if it has 4 congruent sides. Corollary 7.3, a quadrilateral is a rectangle if and only if it has 4 right angles. And corollary 7.4 states a quadrilateral is a square if and only if it is a rhombus and a rectangle. So it uses the first 2 corollaries there. So example 1, for any rectangle ABCD, decide whether the statement is always or sometimes true and explain the reasoning. So AB is equal to CD. So on ones like these, it might help you to draw a quadrilateral. You don't have to make it look perfect. But again, I'm going to call this ABCD. And they're telling us that AB is equal to BC. So let's see here. AB is equal to BC. When from above, ABCD is a square because squares have 4 congruent sides. But not all rectangles are squares. So this one is sometimes true. Okay, the second one, we have AB is equal to CD. So again, I'm going to call it the same way, A, B, C, D. And this time they're telling us that AB is equal to CD. So those two are the ones we're talking about. So what do we know? We know a rectangle is a parallelogram. By the parallelogram opposite sides theorem. Opposite sides of a parallelogram are congruent. So on this one here, okay, remember the question was decide whether a statement is always or sometimes true. In this case, it's going to be always true. All right, example 2, classify the special quadrilateral and explain your reasoning. So if you look at what they have here, we know it's a parallelogram because we have those ones are parallel. And these two sides are parallel. And what else are they showing us? They're showing us that these two sides, consecutive sides, are congruent. Okay. So on this one here, we can say two pairs of opposite sides are parallel. So by definition, it is a parallelogram. So now you see kind of why I use just the two parallel lines instead of writing it all the time. So opposite sides of a parallelogram are congruent. So by the transitive property, and that was in chapter 2, but I did tell you if A equals B and B equals C, then you can say A is equal to C. That's what the transitive property is saying. So it's saying on this one right here, basically it's saying if this side is congruent to this side, and we know it's a parallelogram, so this would be a mark there, and this one is this one, then we can say that all four sides are congruent. And what is a parallelogram that has all four sides congruent? That would be a rhombus. Okay, all right. So theorem 7.11 or 711, the rhombus diagonal theorem states if a parallelogram is a rhombus if and only if its diagonals are perpendicular. So on this one here, it would be saying quadrilateral ABCD is a rhombus if and only if line segment AC is perpendicular to line segment BD. Theorem 7.12 is the rhombus opposite angles theorem, which states a parallelogram is a rhombus if and only if each diagonal bisects a pair of opposite angles. So remember, bisect means it cuts it in half. So if you look here on this one here, they're saying that these two are marked the same, so we can tell that it bisects it. Same here, right? These two here are different, but again, they're both marked with double arcs, so we know that they are the same. So let's write down what it's saying. So quadrilateral ABCD is a rhombus if and only if a line segment AC bisects angle BCD and angle BAD, and, okay, both of them have to happen, BD, line segment BD bisects angle ABC and angle ADC. All right, so BD bisects, cuts in half ADC and ABC, which it does. Okay. All right, example 3. Find the measure of angle ABC and the measure of angle ACB in rhombus ABCD. So on this one right here, we can state that the measure of angle ACD is equal to the measure of angle 2. Why? Here's ACD. It's a parallelogram. What kind of angle did I just make there, people? Yep. The angles, so they're alternate interior angles. All right. So we can state that the measure of angle 2 is equal to 61 degrees. Again, I'll put it here in parentheses, alternate interior angles. The measure of angle 3 is also equal to 61 degrees. Again, by the rhombus opposite angles theorem from above. And then we know that the measure of angle 1 is equal to 90 degrees. And that would be from the rhombus diagonals theorem from above. So the rhombus diagonals are perpendicular. So we know then that the measure of angle, so we've just done 1, 2, and 3. Now we need to get 4. So we can say that the measure of angle 1 plus the measure of angle 3 plus the measure of angle 4 because it's a little triangle there, we know that they equal 180 degrees. So we know that 90 plus 61 plus the measure of angle 4 is equal to 180 degrees. We know that 151 plus the measure of angle 4 is equal to 180 degrees. So again, if I subtract 151, we'll get that the measure of angle 4 is equal to 29 degrees. So do I have enough here to state what the measure of angle ABC is? The measure of angle ABC, that would be this one right here. Well, if we know that angle 4 is 29, we know that this one here was also 29. So we know that both of these have to be the same. So we can state then that the measure, let me put it right here, the measure of angle ABC is equal to 2 times the measure of angle 4, which is equal to 2 times 29, or the measure of angle ABC is equal to 58 degrees. Okay, so we just found the measure of angle ABC. And then it wants us to find the measure of angle ACB. So ACB, well, that one, since this one here is equal to 61, that one there has to equal 61. So the measure of angle ACB is equal to 61 degrees. Okay, next one, Theorem 7.13. So again, look how many, we've just done 13 theorems here, and we haven't proven a single one. We're just letting you guys know that they are supposed to be proven. Again, you would be having to do this if it was a regular year. So a parallelogram, the Theorem 7.13 is the rectangle diagonal theorem. A parallelogram is a rectangle, if and only if its diagonals are congruent. So what that one is stating here is parallelogram ABCD is a rectangle if and only if the diagonals here are diagonal AC is congruent to diagonal BD. Okay, again, it's talking about this diagonal and this diagonal. All right, example 5. There are 6 examples this time, so it's a little longer than normal, but that's okay. In rectangle ABCD, AC is equal to 7x minus 15, and BD is equal to 2x plus 25. Find the lengths of ABCD. So for this, we know that AC is equal to BD. So we can say that 7x minus 15 is equal to 2x plus 25. So again, I'll subtract that 2x, so that'll give me 5x. Now I'm going to do it all in my head in one fell swoop. I'm going to move that 15 over to the other side now, and so that'll make it positive. So 25 plus 15 is equal to 40. And if we divide by 5, that'll tell us that x is equal to 8. So they want us to find the lengths. So they want us to find this one here because that's what we were given, and this one here. So since they're equal, I just have to plug it into one of them. So I'll plug it into AC is equal to 7 times 8 minus 15, which is 56 minus 15, which is equal to 41. So that's what AC equals, but then that also equals BD. So both of them equal 41. And then finally, the last thing we're talking about is when we're using the coordinate geometry again. So recall the distance formula is the distance is equal to x2 minus x1 squared plus y2 minus y1 quantity squared, and all of that is under the radical symbol, so it's the square root. So using coordinate geometry, decide whether quadrilateral ABCD with vertices at A is -2 and 3, B is 2 and 2, C is 1 and -2, and D is 3, -3 and -1, and we're going to decide if it is a rectangle, a rhombus, or a square. Now, it could actually be all three of them. Again, we'll kind of see as we go along, and because it does tell us to say give all names that apply. So step 1, we're going to graph the parallelogram. So we're going to go at -2 and 3. Let me change the color because I want to use my red as my diagonals. So let's go ahead and go to, let's go blue. So A is at -2 and +3. So there's A. -2 and +3. B is at 2 and 2, so over 2, up 2. There's B at 2 and 2. C is at 1 and -2. So there's C at 1, -1 and -2, I'm sorry. So I did write it down wrong there. I have it in my notes as the right one, so I do apologize there. Fix that. No, wait, it's net. Never mind. It is +1. Sorry. I really should stop doing this late at night because it is +1. Because I did go over 1 in the right, but it's -2. And let's see, D is -3, so I'm going to go over -3, and then I'm going to go down 1. So there's D, and it's at -3 and -1. All right, so I'm going to graph it, so I'm going to connect the dots. All right, and step 2, we're going to find the distances of the diagonals. So again, the diagonals are going to be here, and we're going to be here. Okay, that's not asking us to find anything else but the distance. So remember, on that we can write the find the distance of the diagonals. If they are congruent, then we know we're going to have a rectangle or a square. So let's see. So for AC, again, choose one as x1, y1, one as x2, y2, and plug it in. So I'll get -2 -1 squared plus 3 minus -2 quantity squared. So that'll give us the square root of 9 plus 25, which will give us the square root of 34. Now, since it's just asking us what we have, I would just leave it under the radical like that, because you'll see if they are congruent, they're both going to have to be the square root of 34. You don't really have to work it out unless it tells you to, but I don't think it's going to. So on this one here, for the length of BD, not BC, BD, excuse me, we're going to have 2 minus a -3 squared plus 2 minus a -1 squared, which in this case will give us the square root of 25 plus 9, which will again give us the square root of 34. So what we can say, because the diagonals are congruent, we know that our quadrilateral ABCD is either a rectangle or a square. And again, that was from our previous theorems. All right. Step 3, find the side lengths of adjacent sides. If the adjacent sides are congruent, then we will have a rhombus or a square. All right. So if this one is false, we would know we're going to put down a rectangle or square. If this one is true and the other one is true, then we can say that it could be either a rectangle, a square, or a rhombus. So let's go ahead and see what happens here. So again, we're going to take two sides. So I took AB and I took BC. I'm checking to see if those two, I tick marked them, but I'm just checking to see if my tick marks are going to be true or not. So if I take AB, that'll be the square root of -2 minus 2 squared plus 3 minus 2 squared, which will give me the square root of 16 plus 1, which will give me the square root of 17. All right, so BC, for it to be a rhombus or a square, it better also be the square root of 17. So the distance for that one again, I just choose which one. Again, like I said, make one x1, y1, the other one x2, y2. And hopefully I don't have to draw it out for you every single time. All right. So 2 minus 1 is 1. 1 squared is 1. 2 minus a negative, or 2 plus 2 is 4. 4 squared is 16. So in this case, it's 17. So because two adjacent sides are congruent, we have a rhombus or a square. So since they're both true, I just kind of hinted, since they're both true, what would you say? You would say, so quadrilateral ABCD is, from the top one, it's a rectangle. And a square. The bottom one says it's a rhombus and a square. So I just said and a square twice, so it's a rectangle, rhombus, and a square. So in this case, it was all three of them. It's not always going to be the case, but this time it was. Sorry, the notes were a little long, but hopefully that'll help you with your homework.